Welcome, everyone, to Bodhi Unified Flow. I'm Dr. Marmuthu, your host, and here we simplify complexity and amplify performance. Today, we're diving deep into the foundational DNA of sustainable infrastructure. We're talking about the absolute best practices in the design and pre-construction phase. Now, you might be wondering, why start here? Well, the stakes are incredibly high. The built environment currently accounts for roughly 40% of all global energy-related carbon emissions. 40%! Historically, our industry has been kind of obsessed with operational efficiency. Trying to fix things after the building is already up and running. But we're right in the middle of a major paradigm shift. The decisions we make before a single shovel even hits the dirt, those are the decisions that dictate a building's thermal performance, its water consumption, and its overall resilience for decades to come.
So here's our agenda for this explainer. We're going to cover 6 core areas: certification strategy, energy simulation, passive solar design, materials and embodied carbon, water and heat mitigation, and finally, indoor air quality. Our main learning objective today is simple but powerful: to give you a solid grasp of the technical framework you need to drive truly regenerative, net zero outcomes in your projects. Let's get right into it. Section 1, Certifications and Coordination Strategy. Before any lines are drawn on an architect's page, a project really has to establish its foundational DNA. Choosing a certification framework isn't just some branding exercise so you can slap a plaque on the wall. It's about aligning your mission with real, measurable performance indicators. On one side of the spectrum, we have LEED. It's a globally recognized point-based system from the IGBC. Think of it as the international language for sustainability. It's highly valued by multinational corporations that have broad global decarbonization targets. But then, on the other side, we have national frameworks like GRIHA and IGBC. And these are incredibly powerful because they are specifically tailored to regional realities. In India, for example, they address massive local challenges like extreme climate adaptations and severe water scarcity. GRHI actually goes a step further than just heavy paperwork. It mandates physical site visits at the plinth level and at completion to inspect the mechanical installations. This guarantees that your as-built performance rigorously matches your as-designed intent. No cutting corners. But look, a goal without a manager is really just a wish, isn't it? The sheer complexity of a high-performance building means you absolutely must have a dedicated sustainability coordinator from day one. Their job is massive. They manage the interdisciplinary discovery phase, they run technical evaluations on high-efficiency systems, and they strategize around carbon reduction. Crucially, they also act as risk managers for incoming environmental regulations, which are getting stricter by the minute. By managing the complex flow of audit documentation and acting as an educational leader for the contractors, they make sure our green goals don't get lost in the shuffle of conflicting departmental priorities. Moving right along to Section 2, Energy Simulation and Optimization. We are well past the days of relying on guesswork or basic rules of thumb. Today, using advanced software like IESVE or DesignBuilder, we construct a complete digital twin of the building way before construction starts. We run energy modeling to predict annual demand and guarantee compliance with codes like ASHRAE or the IGBC. Then, we use thermal analysis to mitigate thermal bridging. For instance, by optimizing continuous insulation on the exterior, we can actually downsize our mechanical HVAC chillers significantly. That's a huge cost and energy saving. We also run daylight and glare simulations to find that perfect window-to-wall ratio, balancing beautiful natural light without the penalty of excessive solar heat gain. And finally, through CFD, or computational fluid dynamics, we simulate natural airflow. This helps us naturally enhance indoor air quality and dramatically reduce the energy load on our mechanical fans. Section 3, Passive Solar and Thermal Design. Have you ever noticed how a car parked in the sun gets incredibly hot inside? Well, that is the exact basic physics we harness in passive design, using what's called the collector-absorber mechanism. To maximize solar gain in the winter and minimize overheating in the summer, your building should ideally be elongated on an east-west axis. The primary glass area, which acts as the collector, should face within 30 degrees of true south. Sunlight enters through this collector and strikes the absorber. The absorber is typically a hard, darkened surface inside, like a masonry floor or a thick internal wall, which physically converts that solar radiation into stored heat energy. The true elegance of passive design is that these elements serve dual, contrasting purposes depending on the season. Let's look at thermal mass. Think of materials like concrete, brick, or stone as a giant thermal battery. In the winter, this battery absorbs the sun's heat during the day and gently radiates it back into the room at night when temperatures drop.
But in the summer, that exact same thermal mass absorbs the internal ambient heat to moderate daytime temperature spikes. Then, we use natural ventilation strategies like cross-ventilation or thermal chimneys for something called night flushing to cool that mass right back down. Pair all of this with properly sized overhangs that welcome the low-angle winter sun but entirely block the harsh, high-angle summer sun, and you maintain perfect human comfort with just a fraction of the mechanical HVAC reliance.
Now, let's turn to Section 4, Materials and Embodied Carbon. Operational efficiency is absolutely vital, for sure. But embodied carbon, meaning the emissions from extracting, manufacturing, and transporting building materials, is fast becoming our primary challenge. Believe it or not, for certain high-performance facilities, embodied carbon can make up 90% of the total life cycle emissions before the doors even open. To manage this, best practice dictates the mandatory use of EPDs, or environmental product declarations, during the procurement phase. Think of EPDs like nutritional labels for building materials. They are third-party verified documents that give us standardized, hard data on a product's global warming potential. By demanding EPDs, teams can confidently specify low-carbon alternatives. We're talking about prioritizing recycled content, specifying green concrete that uses fly ash or slag to replace cement, or selecting low-emission steel made in electric arc furnaces. And the story of a material doesn't end once it's installed. The industry is rapidly moving toward a circular economy, and the key to unlocking this is the material passport. Integrated directly into our BIM workflows, a material passport is a digital record that captures exactly what a material is made of and its potential for future reuse. This completely flips the script. Instead of viewing a building as a future demolition site full of useless waste, we start treating buildings as material banks. When the building eventually reaches the end of its life, these passports allow us to easily extract, deconstruct, and resell those valuable components.
So, why does all of this material tracking actually matter? Well, the Ellen MacArthur Foundation estimates that shifting to this circular approach, prioritizing deconstruction and resource recovery over traditional demolition, could reduce global emissions from building materials by a staggering 38% by the year 2050. 38%! That is a massive, game-changing lever for climate action, and the amazing thing is, we control it entirely during the pre-construction phase.
Next up, Section 5, Water and Heat Island Mitigation. Let's broaden our view for a second and look at how the building interacts with its vital resources. Water efficiency is all about doing more with less, without making the occupants uncomfortable. During design, we need to integrate comprehensive strategies to hit those rigorous IGBC water credits. This means mapping out robust rainwater harvesting systems and gray water recycling networks from day one. We specify high-efficiency, low-flow plumbing fixtures to drastically cut the building's baseline demand. And outside, we use xeriscaping. That means planting native, climate-appropriate vegetation that barely needs any watering. We pair that landscaping with smart irrigation controls that actually use real-time weather data and soil moisture sensors, so we never waste a drop. Beyond just water, we have to design to mitigate the urban heat island effect, or UHI. You know how cities are always noticeably hotter than the countryside? That's UHI, caused by all our dark artificial surfaces absorbing solar radiation. But the fix is actually pretty straightforward. A standard black roof has a solar reflectance index, or SRI, of basically 0. It just absorbs heat, drives up your air conditioning loads, and bakes the surrounding microclimate. Now contrast that with a cool roof, which uses high albedo surfaces to hit an SRI of 100. Because it reflects solar energy and efficiently emits heat, a high SRI roof can stay 50 to 90 degrees Fahrenheit cooler on a sunny day. When you combine these cool roofs with green roofs and plenty of tree cover, you're looking at the absolute gold standard for urban resilience. Finally, Section 6, Enhancing Indoor Air Quality. Bringing our focus back inside the building, we have to acknowledge a harsh truth. Indoor air is often significantly more polluted than outdoor air, and that has a direct impact on our respiratory health and our daily productivity. So enhancing indoor environmental quality requires a strict two-pronged approach. First, we prioritize source control. We mandate low-emitting materials and enforce very strict VOC limits on all paints, adhesives, and composite woods, so we stop harmful off-gassing before it even starts. Second, we clean the air that circulates. Modern HVAC designs are now integrating advanced UVC air disinfection systems, operating right at a 254 nanometer wavelength. This UVC light physically shatters the molecular structure of airborne pathogens, effectively neutralizing viruses and mold. We then layer this UVC tech with high-grade mechanical MERV 13 filtration, tying the whole system into a building automation system so we can monitor performance in real time.
What a journey we've been on today. Let's quickly solidify our key takeaways. We started by locking in clear goals, using green certifications, and putting a sustainability coordinator in charge. We learned how to optimize our digital twins, how to harness the physics of passive solar design, and how to aggressively tackle embodied carbon using EPDs and material passports. Finally, we looked at how to secure our water resources and protect human health with pristine air quality controls.
Here are the references that informed our session today, covering everything from ASHRAE standards to whole-life carbon assessments. As we wrap up, I want to leave you with this thought. The future of sustainable construction isn't just about doing less harm anymore. By seamlessly converging digital technology, rigorous management, and nature-based physics during the pre-construction phase, we guarantee that the structures we design today become the actively regenerative, sustainable legacy of tomorrow. Thank you so much for joining me on Bodhi Unified Flow. I'm Dr. Marimuthu, and until next time, keep simplifying complexity and amplifying your performance.